In this lecture, we're going to talk a little bit about the at least the numerical processes of analyzing chemical kinetic mechanisms using RMS, with a particular focus on sensitivity analysis. In this lecture, you're going to learn a little bit about more high-level understanding of these different types of sensitivity analyses, how to run sensitivity analysis with RMS, how to choose what sensitivity analysis to use for your application. And we're going to do some demos running some multi-phase simulations with RMS, sensitivity analysis, and automatic mechanism analysis. Um, so nominally, as you've seen, and surely you've seen this diagram a few times before, where we have our initial species, our initial conditions, and we run RMG. And then we analyze this mechanism, and we have our iterative workflow where we look at this and we say, okay, well, are we happy with this model? Is this good enough? Does this have quantitative accuracy relative to our targets? And if we're happy with it, then we go and we get a complete model. But most of the time, most of the times you run RMG, you're not going to be happy with it. The majority of the time, as you've already heard earlier this morning, you're going to want to go and run some quantum chemistry calculations to get some better parameters. You'll add that data back into RMG. And you'll rerun RMS. In other cases, you'll want to go tweak RMG, and we'll talk a little bit about that later today. But what this lecture is going to focus on this box. Or actually, let me get my laser pointer here on this box here on the model simulation and analysis part. So one major part of model analysis is understanding what's happening instantaneously in the mechanism. And you get this from flex diagrams, rate of production analysis. This tells you broadly where flux is going within the system, what pathways are dominating, where mass is moving. And the rate of production tells you about what's producing and destroying any given species. And then the other sort of, this helps you kind of look at what's changed between iterations of the model. And it lets you sort of look at the chemistry that's happening and deciding whether this stuff makes sense and whether stuff's missing. And then the other major component of this is a sensitivity analysis, which is broadly about figuring out what parameters should you be refining, should you be calculating or digging up in literature or taking a closer look at. Now, it's worth going a little bit over what we're actually simulating, what's happening under the hood here when we simulate a mechanism. So nominally, a chemical kinetic mechanism is usually, or for most reactors, say like a constant TP reactor or a constant volume reactor, something similar, is going to be a very stiff nonlinear ODE system. We have some state vector u, which is going to be the length of each kind of the moles for each of the species, plus some set of thermodynamic variables, temperature, pressure, volume, etc. Which is the size of the vector we're simulating essentially in the ODE. Often we'll have tens to thousands of species, so this vector can be on the order of 10 to on the order of 1,000 length. Our parameters here, as we usually simulate it at least, is we're going to usually have one parameter which is associated with the Gibbs free energy of each species, and one parameter that's associated with at least the pre-factor or the forward rate coefficient of the reactions. And so this is going to be length, since this is a length species and this is a length reactions, we've got a parameter vector that's length species plus length reactions. When solving this, it's worth a little bit of commentary on this. There's a variety of stiff solvers you can use to solve these ODEs. In my experience, SIVO BDF stands out as consistently having reasonable cost accuracy and a very low failure rate that I think most of you should be using in most cases. There are other solvers that can work for these that can be like marginally faster. But a lot of them are a lot less robust or measurably slower. Now, when we talk about sensitivity analysis, it's important to get our language right, and especially because we're often very, very sloppy about how we talk about these things. Oftentimes, you'll hear people talk about a species being sensitive or a parameter being sensitive. The correct way to talk about these things is to say that some given species or a state variable, temperature, is sensitive to some given parameter at some time t. Although it's also even a little bit more complicated than this because sensitivity is an integrated analysis, so it's relative to some starting point. So the sensitivity is roughly a measure of how much your state variable would change when integrated from some starting point to some tk if you perturbed this parameter by this much. Now, what's important, an important aspect of this, and about what we're about to get into, is that usually we're not interested in all of the possible sensitivities to every target. If you have 1,000 species in your mechanism, you're not usually interested in what's affecting all of those 1,000 species. There's going to be a handful of U elements that you're interested in, but you're often interested with respect to all of the parameters because you don't know what parameters are going to be important for you. And so we're usually most interested in this case, some target species U with respect to all parameters at some chosen time point t. Now, picking your time point is going to depend heavily on what reactor or what experiment you're comparing to. For ignition delay, you would want to look at the sensitivities right before ignition. Most of the time with experiments, a lot of like flow tube experiments will usually provide the compositions that are effectively at a final sampled time. And so usually you'll be interested in the sensitivities at that final time. Often you can look for basically the most important thing is to not run the sensitivities at a time when no chemistry is happening. That's probably the most key thing, but where you're going to pick that time point is going to vary a lot per reactor. You also want to look at the parameter sources, not just the sensitivities, but also the kind of the rough idea of uncertainties about everything. If they're from groups and rate trees and they're maybe not too sensitive, but might be important, that's probably something you should be calculating. Also, with the RMG libraries, you want to be careful about what exactly this is. What's the level of theory? How well was this calculated? Is it an empirical estimate? Did someone just guess what the number is? Which you can find in these databases and in these papers. Now the first method, we discussed this one not necessarily because we necessarily recommend it, but because a lot of people use it in literature, so it's worth talking a little bit about. So there's some people in literature that swear by this approach, which is what you just do, and it's very simple, is you take each parameter, you perturb it by some perturbation, and then you simulate the mechanism, and you compare it with the simulation without this perturbation to get a delta U at that time point, and then you can compute delta U over delta P. This is a very straightforward way to do it. However, this is not the numerical derivative of U with respect to P, so it's not exact numerically. And your choice of delta P is somewhat arbitrary. It also generally requires we have to perturb every single parameter to get the sensitivity of our interested species. So that's a whole lot of simulations. There are some people that really like this though, because when you do this perturbation, because it's a bigger perturbation, you sample a little bit more global of the space of possible parameters than although it's a very limited sampling. So next we're going to talk about sort of our more focus on the main sort of sensitivity analysis and the tools available in RMS. So there are I would say three main types of sensitivity analysis in RMS. I would separate traditional forward sensitivity analysis, threaded forward, and adjoint, and transitory is kind of in its own category, but I'll talk a little bit about that more when we get there. And we're going to run a sort of different types of sensitivity analysis on the super minimal example together when we get to the end. So first, traditional forward sensitivity analysis we get by just taking our equation, we get our parameter, our du dp, and we take our time derivative. And when you break this down, you just get the Jacobian with respect to our state variables and our Jacobian with respect to our parameters and our sensitivities. And this is a big, giant coupled matrix of equations that's size n species times n species plus n reactions. And better than the brute force, this gets us the exact value, the numerical value of the sensitivities. This gets us these derivatives exactly, or at least numerically exactly. However, and it gets it at all of the time points. So you'll get the sensitivity of all of these things at every time point starting from this initial condition. However, there's some issues with this. This doesn't scale very well. And also, it's all messy and coupled, and usually we're only interested, as we mentioned before, in a single species with respect to every parameter. And this forces us to integrate every species with respect to every parameter. Now, we can do a little bit better by threaded forward sensitivity analysis, essentially parallel sensitivity analysis. Now, if we solve our original ODE and we save that solution and just interpolate on that solution, it turns out we can decouple these equations. And we can break them down into a set of equations associated with the sensitivities with respect to each individual parameter. So we can solve each U with respect to each PJ. And this, the same as before, we get the sensitivity all time points. We can run it in parallel, which is a whole lot faster. This method also scales up very well to very large mechanisms. It's expensive, but it will work. It can operate on very, very large mechanisms. However, we still kind of haven't gotten around this issue. We're still having to integrate the entire system to compute the derivative of every target to every parameter to get the derivative of an individual target to every parameter. And the way you kind of, the math here is not too important that you understand a whole lot of this math. Nominally, you can't really isolate this out in the original equations. But there's a very clever method that does let us do it. Now, and if we take the integral form and we construct this sort of equations, you can eventually develop. I won't go into too much detail on all the individual math, but nominally, eventually you can develop these adjoint sensitivity equations. And what this essentially amounts to is we integrate the ODE forward in time to a given time point, and then we integrate the adjoint equations backward from that time point, these adjoint equations. And these adjoint equations give us this DUI, dP vector that we really want. And this this adjoint equation for this individual target is just the length of n species plus n reactions. And so this allows us to get the p vector directly. We can also parallelize per each target, so we're solving much smaller equations, and we're only solving for the stuff that we care about. And we can solve each of these targets can be done in parallel. It's worth noting this only gives you the sensitivity at the target time point because we integrated forward to that time point and then we integrated backward. So if you want to do it at a different time point, you have to integrate backward from a different time point. However, it is worth noting that this method, it works very, very well in medium and somewhat large mechanism sizes. If you go very, very large, you run into the issue that this adjoint equation is a very hard ODE to solve. And so when you have a very, very large coupled mechanism with a very, very large parameter vector, you may be better off with the threaded sensitivities. It won't be fast. I mean, it will be much more computationally expensive, but it's a little bit, adjoint starts to break down when you get to really, really big stuff. It's for transitory, I think it's important to go through a little bit of motivation. So the sensitivity methods I've talked about so far give you these exact numerical sensitivities as we've defined before. It's the sensitivity of UI to some parameter at a given time point with respect to some starting point that you integrated from. However, and with adjoint, you can get medium-sized mechanisms, say the methylpropyl ether mechanism, about 500 species, you can get the compute time down from 4 days to about 4 hours. However, 4 hours is quite a while to wait. And maybe more importantly, for very, very large mechanisms, this sensitivity computation can become really, really challenging. It can take a really long time, even with these adjoint and parallel methods. And additionally, another sort of important aspect is that when you're usually analyzing, when you're looking at rate of production analysis and you're looking at these flux analyses, they're all at a given time point. You're taking a snapshot of the system and looking at where all the fluxes are going. But for these sensitivities, because they're integrated, they're difficult to reconcile with these because the sensitivities are dependent on a lot of different things that are going on in the system. So when you want to map the sensitivity back and say, oh, this is sensitive because of X or because this is going on, it's not so straightforward because the sensitivity involves a whole lot of all of the chemistry occurring between the starting point and the end point of the sensitivity integration. So suppose instead, instead of looking at what's sensitive, we look a little bit at we think about what's increasing in sensitivity at a point. And there's some nuance to how you do this because you're in a stiff system and you need to relax some of the faster dynamics. But nominally, if starting from those forward sensitivity equations, you can break this down and get some sort of rough system, some sort of relax over some time scale tau, some essentially the average value of the sensitivity with respect to time. And with some clever approximations, this can be evaluated very, very efficiently. If you look at this comparison here, comparing sort of the traditional sensitivities to the transitory sensitivities, the transitory sensitivities are very solid at finding these traditionally sensitive reactions. As you look here, we only did transitory sensitivities at 2 time points. And we're able to find all of these sensitive reactions here, which is notable because transitory is this idea is very significantly different because this is going to get you sensitivity at a very local time. What's important about what's going on at this specific time point instead of this integrated analysis. Very important, one important aspect of this is about 18,000 times faster over adjoint sensitivities, which makes it very easy. So instead of waiting 4 hours, or in dodecane waiting days, you can get these sensitivities in milliseconds to a minute. It also lets us do some a little more fancy stuff. So since we have these transitory sensitivities and they're at a time point, and we have our rate of production and our flux diagrams and they're at a time point, we can fuse these, which allows us to automatically identify these sensitive reactions. So we can say, okay, we run transitory sensitivities, we find our sensitive reaction here, and then we can go and run our flux analysis. We can look at the branching for this species and this species. So what other reactions is methylpropyl ether running, this MPE? What's producing it? What's losing it? What's it affecting of the branching for this species? And it can detect whether or not what branchings are important and output them, and also sort of the key paths that are causing loss for each of these, which are kind of the different reasons. Because usually something's going to be sensitive because either it's part of a branching. It has a nominal value that if you move this rate coefficient, you can change the branching between multiple pathways, or because it's controlling the rate at which flux can go through a given pathway. And then additionally, you can also have sensitivity because it essentially moves between different clusters, which is conceptually a little bit difficult to talk about. But if you think about it, reactions that produce radicals in general matter a whole lot in radical chemistry, and have a significant weight of importance and sensitivity above what for relatively little flux, because they're producing these reactive species. And this can help you significantly at sort of figuring out these mechanisms, and looking at, and at least putting the information that you should be looking at in front of you to sort of figure out what's going on. Now a little comparison of these, just sort of a little bit of a reminder. These three are numerically exact sensitivities here. Threaded forward and traditional forward at least nominally scale the same, but threaded forward is in parallel, so it'll be a little bit better. These ones all give you all sensitivities with all sensitivities of all state variables to all parameters at all time points. Adjoint gives you a given set or a given target variable, the sensitivity of a given target variable to all parameters at one given time point. Transitory is nominally gives you the transitory sensitivity of all targets to all parameters, but at that time point, and it's not numerically equivalent to these sensitivities. It doesn't even have the same units. Transitory is incredibly fast, but of these, adjoint is nominally the fastest way to get sensitivities in most cases. And threaded is also I would say the implementation in RMS. Threaded has a much better implementation than traditional forward. So even if you're not parallelizing, the threaded forward will be a lot faster. How to choose sensitivity analysis. So usually if you don't, my recommendation is nominally that if you don't need the exact sensitivities, you're probably transitory can probably do your job for you. You want to sample at a few different points when you do it. But as long as you're doing that, it's a very fast and easy way of looking at things. It's also it's a lot easier to reconcile with the flex diagrams and stuff that you're looking at. However, if you do need the real sensitivities, and there's a couple of very good reasons why you might. One advantage of sensitivity is combining the sensitivity and uncertainty analysis. If you take the uncertainties and multiply it by the sensitivities, you get some rough measure of how much that target is affected by that parameter. And with that, you cannot use transitory sensitivities for that kind of analysis. And so in those cases, you'll need exact sensitivities. Also, these can be nice to put in papers. If you don't need it at all times and for all species, usually you're going to want to use adjoint. If you do need everything, you should go to threaded. You should also go to threaded if you're doing something like incredibly large, like thousands of species. Adjoint may have some trouble solving the backwards adjoint equation in some of those cases. Yeah, so transitory focus kind of in the loop usually, and then adjoint or threaded when you need the exact sensitivities. Yeah, so a little bit warning about model analysis. I talked a little bit about this in the last day of this workshop. These rate coefficients have three regimes: so fast that it isn't close to rate limiting and dominates any branching, so it's insensitive, or so slow that no flex goes through it and it doesn't affect branching. And these rate coefficients are only sensitive in that in-between regime. Oftentimes, the uncertainties in these kinetics are large enough to bridge these regimes. So you do want to calculate some of the species that are not in this in-between regime, because they might actually be in the real regime, especially if they have large uncertainties. These sensitivity analysis methods are going to miss important chemistry that falls in those so fast and slow regimes, because it will find them if you have the exact right parameters, but in reality, you're not going to have the exact right parameters. So in a lot of cases, some of the reactions that you need to calculate may not be found by these local sensitivity analysis methods. It's also worth noting that these tell you what, not why. That's kind of why I'm pushing transitory sensitivity analysis a little bit more here, because it's a little bit easier to interpret. It's a little bit easier to map straight on to your flex analysis and ROP analysis. And those are key to sort of helping catch things in this so fast regime. Although it's often not so helpful in the so slow regime, because it won't show up on your flex diagram. This is also kind of goes back a little bit back to this, sort of putting sort of the traces here for the branchings and for the reaction paths, which can kind of help you put the information out there and point you to sort of the stuff that you should be taking a look at. Okay, so next we're gonna do the sensitivity, these example notebooks. hopefully this is the same as last year. But let me we'll do the I need to unshare. So if you can run this notebook, run these imports. I won't run them now. Are we good to go on this?
It looks good to us in the room.
It's the stuff's working, stuff's running.
Matt, we can see it, but I was unable to get it to run locally, but you can try to do the import. And if it doesn't
I mean,
work,
it will work on my computer. I know that. I've tested it on my
I'm
computer.
happy to watch Matt do it.
Um, um, so nominally, I mean, we load our mechanism. We give it our initial conditions, our time that we want it to span. We build our phase, our ideal gas, our constant volume reactor here. And our reactor, we run our ODE solver, we run SIVO BDF here. And we post-process that simulation object. And then we can, so transitory sensitivities is very, very fast, as you can see here, although everything's going to be very fast with the super minimal one. And we can get our reaction transitory sensitivities, which kind of points you to these, which reactions are the most important here. We can also do thermochemistry here, which tells you what species thermochemistries are the most sensitive. And then adjoint, where we give it our specific species we're targeting, because adjoint is with respect to a specific target.
Matt, can you hear us?
Yes.
You had to choose the time at which you evaluate the sensitivity, is that right?
Yes.
Yes. Okay. And how did you pick that? Or how would
Because that's the time of the simulation of the reactor. So because it integrates backwards, we just feed it the simulation and then it integrates the adjoint backwards from it. So this simulation was run for a specific time span here.
you just chose to do it at the end? If
Yes.
someone's doing like an ignition delay or something, then the end everything's just exhaust gas. Would
Yes.
they get
I would suggest just running it once and then figuring out how long to run it out and then just simulate it again, which usually isn't going to take very long.
Right, but then for the sensitivity, to get useful results that you can interpret, is it important to kind of pick an interesting bit chemically, like pre-ignition or something?
Yes. Oh yeah. Or yes. Well, especially for adjoint because you're picking your time point. For transitory, yes, you want to kind of sample around. Although what I would say is that you have to be careful around ignition, because with transitory because it's an instantaneous analysis. For integrated sensitivity analysis, you have the memory of all the chemistry that you've integrated through. So for transitory, you need to be just a little bit before, because ignition is a very messy time for the simulation. And it's also not so useful for an instantaneous analysis because if you're caring about ignition delay time, you care about the radical buildup before that leads to ignition, not the actual ignition point. Does that make sense?
Yeah.
So you want to be, the problem is this is such a simple example. Yes, question.
What kind of reactor this software supports? Is it like a constant container or there are many different kinds of reactor or reacting scenarios that this software would be compatible with?
This is an excellent question. It's in the slide deck. If you can just bear with us for a little bit, we're about to go through all of that.
Okay.
Yeah. But let's let's get these running. So adjoint's finished now, and we can get our actual numerically accurate sensitivities and our thermo sensitivities. But of course, this is we're taking our output here from this. So this is specific to our target. This is specific to the hydrogen sensitivities. And then we can also run threaded forward sensitivities, which we start from our simulation, and it runs the sensitivities out to there. And as you can see here, we get the same results. And then you can also do traditional. I don't do traditional. It's worse in every way than threaded sensitivities. But should give us the same results here. So we're consistent, right? Good sign. All right. Let's get back and answer that question there. So to answer that question, so RMS is a simulation software. It's designed to sort of put together sets of building blocks into an overall reactor. So the first part of this is you have the phase object, so this is going to be your gas, liquid, or surface, which controls how thermochemistry and kinetic parameters are computed. So within gas phase, liquid phase, and the surface phases. The liquid phase can account for diffusion limited kinetics. And so you construct each of these phases differently from your species and reactions. And then out around the phase, you have the domain. And so the domain essentially controls what assumptions are made about what's going on in this system. So for ignition delay, you might assume that the volume is constant, but assume that it's adiabatic. So that would be a constant V domain here. If you were in a flow tube reactor and you just wanted to assume that it was constant temperature and pressure, there's also a constant TP domain, but there'll be a table with all of these there. But nominally, the domain controls what assumptions are made about the thermodynamic state of the system. How do temperature, volume, pressure, etc. evolve in time as reactions happen? We also have other building blocks that let multi-phase systems. So these interfaces essentially provide modifications to the domain or interface multiple domains to make an overall reactor. So we might have so for here we might have an inlet to our domain, that defines some flux, or some flux is a function of time. Into this domain, or some heat, or you could have some heat flux or something along those lines. And then you could also have, so say you're simulating a catalytic system, then you have a surface and you have a gas phase. So you're going to have a surface phase, a gas phase, and each of those are going to have a separate domain. But of course, you have reactions of gas phase species reacting with surface species. And so we have these reactive internal interfaces that handle these reactions between each of these domains. And nominally, this is designed so that you can build a reactor that looks like your actual real system that you're trying to deal with. And then we wrap the overall reactor object around the interface, these set of domains and interfaces. Which figures out how to handle the numerical details, constructs the ODEs, decides what's the best solver configuration, which is CVOD BDF, but there's a couple different ways you can configure CVOD BDF, especially like handling preconditioning. Commonly with an ideal gas, you might have a sort of flow tube reactor, which might be a constant TP domain. A constant V domain for sort of RCM, shock tube, ignition delay type experiments. Other people might simulate shock tube with a constant P domain. And then there are other cases, like if you know what the temperature pressure profile is, you can use it to do a parameterized TP domain where you tell it in advance what the temperature and pressure are going to be in time. And you can do the same with volume and with pressure. If you have those traces, which this is important in that case I showed in the RMG recommendations lecture. And then for ideal dilute solution, you're often going to use a constant TV domain for these cases, or a parameterized, if you're going to parameterize the temperature, the parameterized TV domain for most of these, more of these liquid phase type reactors. And then for ideal surface, usually you're using the constant TA phi domain for the reactive surfaces. So for the single phase or single domain interfaces, you have inlets, outlets, volumetric flow rate inlet, volumetric flow rate outlet that essentially allow you to move mass into the reactor and pull mass out of the reactor or your domain, or sorry, to be more technically specific, your domain. And then also for interfacing with sort of like if you have a liquid and you're interfacing with an over gas phase, handling condensation evaporation with a reservoir that has a constant concentration. And then for multi-phase, we have these reactive internal interfaces for both the variable temperature and constant temperature cases, and then also sort of this vapor liquid mass transfer internal interface reactor for thermal cracking space cases. So we super minimal example. I was showing you the sensitivities to this before. And that'll look something like this. The flex diagram, the ROPs, and the mole fraction in time. So here's a more complicated example where we have a much more complicated, this sort of motivates a little bit more of having the flex diagram so that you can look at and see what species are doing in all of these cases. Where things are a little bit more complicated. So this is a little where we have vapor liquid mass transfer, and these vapor liquid simulations, a lot more complicated case that we've done with RMS. And here, this is the demo that I'll show in a second for catalysis, where we've got both a surface and a gas phase. Let me. So in this case, we load our catalysis mechanism. We've got 12 gas phase species, 3 gas phase reactions, 29 surface species, 198 surface reactions, and 21 gas surface reactions. We tell it our temperature, we decided temperature, pressure, the area of our reactor, our site density on the surface, our area of the surface, site density of the surface, our initial conditions for the gas phase. So here we have methane and oxygen and nitrogen. And then our surface conditions, where we're just saying that it's vacant initially with this area and this temperature, and our time span of how long we're simulating. So we run that. We make we construct our phases here, telling the surface what its site density is, and we construct our individual domains. For each of those, our interface that deals with all those reactions between the surface and the gas phase. And then we feed in our ordered surfaces. So our gas phase, our catalysis phase, gas phase, catalysis, initial conditions, our interfaces, and then the parameters for each of those. We solve that each set of equations. We make a little more complicated system simulation object that handles having multiple domains. And then we can solve, in this case, we're solving for the first one, which is our surface here, and our gas phase. This is the second one because it's indexed to 0. And then our first one, which is the gas phase. And then we pick a time and we can tell it to pull up a flex diagram here, which lets us sort of trace what chemistry is happening, how this stuff's breaking down. Where yellow is more chemistry and the darker is less flux. And then also we can plot these ROPs. We pick some species that we're interested in what's producing and causing loss for it. And we can see what reactions are. So for OX here, we can see that it's being lost. It's primarily going away by reacting with hydrogen to make HOX. Any questions about this notebook?
Yeah.
Actually, I've got a,
Is the outlet?
Yeah, it's the owls.
Yeah, it's fine. You can just shout, yeah.
yeah, just curious, Matt, just if you personally, if you prefer for your, workflow to use the, Python interface, or do you primarily do your coding in Julia at this point?
I primarily do it in Julia. If we could have, so what I would say is, I think we probably should do this. I mean, Julia isn't, for most of the steps here, it's relatively easy it's not that hard to do in Julia, especially if you're pulling from an example. I would generally recommend running in Julia. Also, if we had done this example in Julia, it would have worked. So that you guys wouldn't be having this trouble if I'd rewritten this in Julia. In general, I think it's better to do it in Julia. The reason why we've done this so far in inside through PyRMS, the wrapper is primarily just to try and make it easier for the workshop so that we aren't changing languages. Which is good. But on the whole, I would recommend running it in Julia. I think it works. It's a little bit easier. PyRMS is a pretty good wrapper, but I think we've made some changes in how RMG interfaces with it, which is probably why you guys are having trouble running the examples. It's a little bit it also, the errors are a little bit easier to read. If you get an error message, what you get through the Python wrapper of all of it is not quite as easy to deal with as the direct Julia error if something goes wrong. Any other questions on this example? Okay. Or is there something in the chat?
Oh, where to get the notebooks?
I had copied mine into the chat yesterday.
Yeah, so some people were having issues with it accessing the Dropbox. We'll send out the materials after the workshop to figure out how to properly address that. Matt, if you wouldn't also mind like sharing this next Jupyter notebook in the chat, people can access.
Okay, yeah. Let me let me just read this slide and then I'll do that. So the third demo that I added this year, which is a little bit to show a little bit of the automatic mechanism analysis toolkit, so this is a little bit larger mechanism that shows this off a little bit more. So this is a simpler system. So this is just an ignition delay system here where we've got some temperature profile, and then we're at constant volume building up radical concentrations, and then the temperature spikes when the fuel ignites. All right. Okay, let's see. Okay, I think that should be the file. Let me. All right. Okay, good. Yes, this is the right notebook. Here we're gonna load this propylmethyl ether mechanism. This is much larger. This has about 450 species ish. So it's gonna take a little bit longer to load here. We've got our initial conditions. We're starting at 700 Kelvin, 15 bar, with stoichiometric PME and with air. Or actually, oh, never mind. Sorry, this is an experimental. This was a specific experiment. I think, where we had argon in there. We build our ideal gas phase here. And then we're going to build our constant volume domain. And our little reactor there around the domain. Taking a little bit longer. The ones we did before here were very small. But it's optimizing the mechanism a little bit right now. But I'll talk a little bit. So we've got our temperature profile. So when we're doing this automatic mechanism analysis, we want to look at these. First, you kind of want to look at these simulation profiles and see picking where your time points that might be useful to run transitory sensitivities at, or time points to run this automatic mechanism analysis at that I'll show you. So where in this case we look here and we might pick this sort of when the chemistry is just, oh, sorry, you can't see because I don't, or at this 0.012, this is right after the chemistry starts to trigger and starts to start happening here. This isn't the only important time point here, but it's one point that you would be worth looking at. You also might want to look at one a little bit later, closer to ignition. There's a lot of chemistry in these ignition delay. There's a lot of different chemistry that happens. There's a significant regime change as you're moving along this profile, so you need to sample a little bit there. It must be JIT compiling something. This should only take a couple seconds. But anyway, so we might pick our fuel as our target, and we might pick that time point. Okay, there we go. We make our profile, we take a look at it, pick our target. We're gonna want to do this for a couple different targets just to take a look at things, and our time point. And then what we do is we tell it we want to do this analysis. We want to analyze this specific species, our target, at this time, and we tell it how many sensitive reactions we want it to go through and look at and examine. And what it does is it goes through and it tries to figure out what it looks at what it runs transitory sensitivity analysis and it identifies reactions that are sensitive. And then what it does is it goes through, it looks at branching, it looks at reaction paths, and tries to reject hypotheses about why this reaction is sensitive. So in this case, it considered that this reaction is that it's high flux enough. It has a branching that's sort of in the intermediate region, so it's not really, really high or really, really low where it would be insensitive. So it's possible that this reaction is sensitive because it's affecting branching for where OH is going. Which is definitely true for this. It's also important for branching about where the fuel's going, what the fuel is turning into. And it also says that it might possibly be involved in how propyl-methyl ether is being destroyed. And here you can look at sort of the path branching of each of these, so you can kind of see how much flux is being lost in each of these steps along kind of, this follows the main flux path. So following the largest fluxes as you follow down through. So this is a way of looking at these reaction paths, but the branching tells you a little bit so you can see here, about more than half the flux has leaked from this path, and when we go through this particular step of the mechanism. And this can point you to reactions that are part of these main paths that are important, that might not be sensitive, but are part of these important key paths that are sensitive. Because even if this path is even if this, suppose this reaction was important, but it wasn't sensitive, usually something in that path will be sensitive often. And so this sort of can help us point towards reactions. These branchings also the same, can point you to stuff that isn't sensitive, but might be if its uncertainty is high enough. It has the possibility that it might be important. And this can be helpful. So this one looks somewhat similar. This is also another OH branching reaction, a very important reaction. But there's also some other ones that are a little bit, if we go down here, so you can see with some of these, it has hypotheses. It's rejected a lot of these hypotheses. So for this one, it doesn't think it's important for following the flux, but it does think it might be important for this key branching, which gives you a little more information. And then it'll also find these ones, which are, so as you can see, this is breaking this OH bond and making two radicals, which makes a net radically production function. And if you look at it here, it's accounting for 17% of net radical production, and that's why this reaction is important. The stuff up here looks a little bit more complicated, but that's a system that's designed to handle when the reactive species isn't necessarily a radical. Which is, when it's a radical, it's nice because RMS knows that it's a radical. So it can just say, oh, are we producing radicals or not? But in other cases, we have a clustering algorithm that is able to intuit that out. As you can see here, it gets a pretty similar number to the radical production. But nominally, this can be very helpful for these large mechanisms when you're trying to figure out what's going on and what stuff you should be looking at, especially if you're not very experienced and don't have like a good chemical intuition for a lot of this stuff yet. Any questions on this notebook?
The question. I'm still struggling a little to get from what we're seeing on the screen to what you'd, I don't know, tell Bill or write in a paper or put on a slideshow or something. Like, what's this really telling us? It's a poorly phrased question, and maybe it's impossible to answer right now, but that's what I'm struggling with at the moment.
So in general, when we're trying to analyze a mechanism, we want to figure out there are going to be important there's a lot of reactions that are important, that are sensitive, and there's a lot of reactions that maybe could be sensitive, right? What's important, and the way we intuit out a lot of these is by looking at the mechanism, is by these flex analyses and ROP analysis, and going in and looking at all of these. What this kind of helps you do is it helps sort of put a lot of this stuff right in front of you. This is a very it would probably help if I showed the molecular if these were named a little bit better, certainly. Which may be something worth thinking about. But what this is designed to do is to put in front of you. So where OH goes in a combustion mechanism is really, really important. And this is pointing you directly to that. It's saying, okay, well, what are the way this reaction, and initially you might not know what directly to look at, but this figures it out because it runs a transitory sensitivity analysis and it says this, okay, when I wiggle this, it's really important. So let's look at what this is. What's going on? What's this reaction do? What does this reaction do in our mechanism? And it says, oh, okay, this affects how OH branches, where OH is going, which is something that I think those of us that are at least have done a lot of combustion mechanisms know this is very important. And it takes you right there and it says, okay, this might be important because it has this really high branching, it has this medium or at least medium branching ratio for this. And there's also these other reactions here too. And maybe this reaction might have a really bad, but our uncertainties for a lot of our estimates can be 2-3 orders of magnitude for a lot of these rate coefficients. 2 orders of magnitude takes this from 0.02 to 2, which would dominate this branching, right?
Are those other reactions just there for context? Because they weren't the original reaction that it started to analyze.
Yes.
So they show what else, so we can compare it.
It's both to compare it, it's also to kind of give you an idea of what's like what we're essentially doing is we're exploiting the transitory sensitivity's ability to find what's important, what seems to be wiggly in the mechanism in a sense, what's in the vicinity of something that's sensitive, right? And then we're kind of expanding around it and looking at these sort of exactly. So this also tells you kind of what happens is that why I think that like this reaction, this tells you to someone that isn't experienced might look at this reaction and not really understand why it's sensitive. It's not very high flux. So why is this important? And this tells you pretty much right away what this is important. This is affecting net radical production. And with this one, it's saying, okay, immediately, this is probably because it's affecting these sort of branching ratio, the branching ratio for this. When we make this species, what happens to this species, right? Which tells you some information, and then it also provides this kind of expansion around, which tells you, okay, well, this is the important chemistry. Here's some of the related stuff that's around this that might also be sort of important, because from the sensitivity, we're really only measuring, as I said before, with sensitivity, it only tells you what's important. It doesn't tell you why, which is a real flaw in it, right? Because you can run these sensitivity analyses and then you just say, okay, well, it's sensitive. It's when we wiggle this, something happens. This kind of helps. The intention of this is to connect the sensitivities with what's actually happening in the mechanism. And also just sort of put some of that information, sort of point out sort of like what's going on, and also point out some of the stuff that might be important, like these pathways, pathway reactions that they may not be sensitive, but they're part of a key reaction path. So you may want to calculate them anyway, right?
This is really helpful for someone who's trying to make their mechanism better, not just explain a good mechanism and what it's doing.
Hopefully it does both. A little bit of both.
Thank you.
Okay. Any other questions on this?
I just talk
Hey,
loud.
Matt.
Yeah.
I'm curious if you were looking at, say, like a steady state flow reactor, if you could somehow reformulate this type of sensitivity as like a function of distance instead of time. Or if you could just say like, there's this time, so the gas is at this point in the reactor or something, I don't know.
You're in a reactor that's entirely at steady state, so it's not it's not about the same time.
Process, right?
Yeah.
Catalytic packed bed.
Sorry, I couldn't hear that.
Catalytic packed bed reactor.
The two models of PFR, like a 1D.
For the PFR, so PFR also is equivalent okay, so the catalytic one is a little bit not equivalent, but you can devise a reactor that is equivalent in time. So essentially you can swap distance for time. So like in a flow reactor, the little simpler case, suppose you have a gas phase flow reactor. It's at constant, say you're at constant temperature, constant pressure. And nominally you're simulating in your reactor is in space. So you measure at say like 10 centimeters down the tube, right? You have that's where your detector is. But what you can do is if you know your flow rate, you can just say, okay, actually this is since we're keeping constant temperature and pressure in this, we're going to just simulate in a batch reactor that has the same temperature and pressure. And that will give you the exact same simulation as that. Does that make sense? So for the plug flow, there's an equivalent reactor set. It's a little more complicated, I think, in the packed bed because in the packed bed, usually you want the surface to be at steady. You want the surface to be at steady. You have a DAE instead of an ODE because you're going to have the surface be at steady state, right? Does that answer your question?
Yes.
Okay. Any other questions? Also general questions on all of this. I don't think there's that much left in terms of the slides. Oh, and okay, good. Yeah, and we're slightly over again. Nominally, so a lot of this is in this RMS paper. Also there's also the transitory sensitivity paper that isn't here. But and then also the documentation for RMS is available online. Yeah, any last questions before we close this session out?
RMS, it's in the Docker image or the newest ones, right? I know that 3.2, but the latest has RMS in it, or a version of RMS. I guess we'll be constantly updating that. But it's kind of most people already have it and can like they shouldn't think there's a huge barrier to using this, right?
Yeah. The version that's probably in the Docker image is the only newer stuff is the electrochemistry stuff. In RMS, I think is the primary thing that probably wouldn't be there. The V 1.1.0 or 1.0.1 is pretty yeah, very stable.